Hello friends, today we will see the topic antenna, where this specific topic in that the antenna is defined as a usually metallic device as a rod or the wire for radiating or receiving the radio waves. The IEEE standard, the antenna or aerial as a mean for radiating or receiving radio waves. So basically the antenna is a metallic device which is used for radiating or receiving the specific radio waves. This antenna is a transition device or the transducer between the guided wave and a free space wave or vice versa. Whenever it converts the electrical energy into the electromagnetic waves, it is called as the transmitting antenna. Whereas if it is the electromagnetic waves are converted into the electrical signals, then it is called as the receiving antenna. There are different functions of the antenna we can observe. In a transmission mode, it is used to radiate the EM waves, whereas in receiving mode, it sends the EM waves. An antenna has a function like a transducer, convert the electrical energy into the EM energy, and again it converts the electromagnetic energy into the electrical energy. Another main important feature of that, whenever it radiates the signal, it is travel through the particular guided medium and it will be released in a free space. Then another requirement is that the maximum power should be radiated in a specific direction. So the antenna must also serve as a directional device, means it should radiate more in the desired direction, more power in the desired direction, and suppress the unwanted directions. Then another thing is that here the figure shows the particular EM waves. It is the electric field which is available over there, and here are the four different components we get it here. So first one is called as the source, which is operated by the voltage and it generates some electrical signal. Then it is a transmission line where the electric fields will be developed here. This is the maximum electric field where the particular crunching of components takes place, whereas this is the negative component, so negative peak level, where it is the reaching to the zero level. So here corresponding to that we are getting the EM waves. Okay, so these waves are guided through the transmission line and open by the flare, which is normally called as the antenna. Now whenever the particular oscillation takes place for this particular signal which is applied to the antenna, because of that the electrical field will be developed over there. So the first positive half cycle, for that the polarities are upper part is positive and below part is negative, so it will be moved from the charge will be moving on from positive to the negative, so it is downward direction. And then it altered the charge from positive to negative and negative to positive. So here it's a negative and here it's a positive. So it will move the charge from positive to the again negative. And after successive oscillations of the signal, these waves will be in a closed form, and it is radiated in a free space. Then this is the equivalent circuit of particular antenna, where the transmission line Thevenin's equivalent circuit is available, where it is the generator which having the impedance of ZZ, which is normally the source. Then this is the transmission line where the signal is guided properly, and this is the part of the antenna. So here the transmission line, on that the particular signal is travel and it will be accepted by the antenna. and it will be radiated through the antenna itself. So here the component of antenna are load resistance, radiation resistance, and the X of A is the reactance of the antenna. So these are the three different components we get it. So the antenna impedance is represented as the addition of RL, that is load resistance, plus radiation resistance, plus J of XA, that is the reactance of the antenna. Then impedance of real transmission line. Now normally the transmission line act as a guided media for the antenna itself, and that's why there are different impedances available for the particular transmission line, and that's why depending upon your applications your different impedance requirement is there. And that's why the first one is the 50 ohm, which is required for the array for microwave lab. Second one is the 75 ohm, which is required for DTH antenna, direct to home antenna, to set-top box converter, Yagi-Uda antenna to the TV receiver or the cable TV. Third one impedance is the 300 ohm, which is the twin lead or flat Yagi-Uda antenna to the TV receiver. Fourth one is that it is the 600 ohm, which is required for the telephone line. Now here the figure shows that here is the radio transmitter is available whose characteristic impedance is 75 ohm, and here it's a dipole antenna is available whose characteristic impedance is the 300 ohm. Now normally here it's a mismatch between the 75 ohm and the 300 ohm, so we require the impedance transformer whose characteristic is the 150 ohm. So by looking from this side, the 150 ohm plus 150 ohm is the series component we get it, and that makes a 300 ohm. But looking from this transmitter side, if you observe one, this act as a parallel component. So 150 plus 150 parallel with the 150, that gives us the 75 ohm. So this is the particular impedance matching component between the 75 ohm and the 300 ohm. Then normally the impedance requirement, why it is the 50. So if you see the particular characteristic impedance, that actually determines the relation between the voltage and the current waves, and Z0 is function of a physical dimension of epsilon r, as well as the Z0 is usually a real impedance, which is the real value, either the example is a 50 ohm or the 75 ohm. Now here is a graph shows that the particular X component where the characteristic impedance is changing from 10 to 100, whereas the particular we can say the normalized value is available here from 0.5 to 1.5, and this is the normalized value is available here 1. Now two important parameter we focus on that. The number one is that the power handling capacity peak value. So here this is the curve where the particular it should be grown up properly, it reached to the maximum value, normalized value, and then it will be dropping over there. So it shows that the maximum power handling capacity is available at 30 ohm. But at the same time, if you see the behavior of the attenuation, it will be the very large enough one over there. And that's why here if you see the characteristic of attenuation, 30 ohm at the value of that, it will be maximum and deteriorating one and reaching to the normalized value one at 80 ohm. Okay, now in fact for the antenna we required the particular power handling capacity should be maximum. At the same time we require the attenuation that should be minimum one. So there is a trade-off between the power handling capacity and the attenuation. We should not select neither 30 nor 77 ohm. So the trade-off between that should be the 50 ohm standard, and that's why we need to select the characteristic impedance 50 ohm, which is the perfectly handling the power with the minimum attenuation loss. Then another component of the antenna is the power transfer efficiency. We know very well that the power is only transmitted maximum one only when the maximum power theorem is hold good. And that's why in that case the particular impedance matching we required one between the load impedance and the source impedance. At the same time, if any reactive components is available, then it should be the complex conjugate of each other. And then and only then, if this condition is satisfied, then and only then we get it the maximum power at the desired value at the final end. Thank you. Thank you very much.